these lecture notes, first things that I want you to do, please go through and number the slides. So when you number them, I'll jump back here because I know this is where I have it. What you'll do is this would be number 1, and then this would be number 2. And then going down, this would be 3, and this would be 4. So you go left to right and then down the page. Yes, so 1, 2, 3, 4. So if you could go through, just take a second, and that way I can refer to slide numbers in terms of whenever you're absent, how many slides I did, as well as, wait, there are no more binder quizzes. No, I only do quarter 1, quarter 3, that's it. Yeah? So, just for fun.
Easy grade.
Yeah, I actually considered switching them to like not waiting until the end of the quarter, but doing like a mid-quarter 2 and a mid-quarter 4. I thought about that this year, because that way it would be closer to the end mid-quarter 4. Yeah. Yeah, I did end of 1, like end of first quarter and end of third quarter, but like I could shift it by 2 to 3 weeks and still do 2. What's up? I know, that's what I'm saying. So like I could shift it, and then the quarter 4 one wouldn't legit be your entire binder. Yeah. Anyhow, I used to do this unit before the quarter 3 binder quiz though, which is why numbering slides was helpful. All right, so there should be a total of how many slides when you're all done? 33, you quick numbering people. Yeah. All right. So I'm going to be writing stuff on the slides, but obviously you have your margin space as well. So if you need to move into that space, please do so. But you know, I've done the notes on your paper as well, even though it's going to look a little different on my screen. Yeah. All right, so here we go. If you are studying, it's nice that we have a little almost like table of contents at the front here about what this particular section of your notes is going to talk about. It is going to talk about voltaic or galvanic cells. It's going to go through an explanation of what voltage is actually measuring, what it is. Then we're going to talk about the standard reduction potentials, a way for us to measure voltage of half reactions, as well as being able to calculate standard cell potentials for these voltaic or galvanic cells. Yeah, so a number of different things going on here. All right, we begin first with a, I'm going to zoom out more here, an equation, right, that you guys have. And does that look that way on your sheet? I forget. Yeah, and I believe what I did is I had whited it out. That's probably what's happening right here, because that t should be a lowercase t, I guess is what I'm getting at here. Is it should be a lowercase t, meaning over here, this should be a lowercase t, because that's what we use for time. A capital T is generally for temperature, so I think that these notes are inappropriate in that sense. Also, this is on your formula sheet. It's going to be really zoomed out, but it's on your formula sheet down here, and notice they also use the lowercase t, right, for time, because that is standard. So that's just an issue with that particular slide. All right, so electric current, right? We're going to be generating electrical current using chemical reactions. That's what electrochemistry is about, is using chemical reactions to generate electrical energy, right? So if we want to measure electrical current, here is our definition of electrical current. It's the amount of charge that passes through the cross-sectional area of a medium per second. So I do boil it down to charge per second. Right? It's how much charge is going past a point per second. So looking at my formula here that apparently is going away. Oh, there it all comes back now. Let's undo that then. Stop it. Whatever. Go away. Okay. This should be a lowercase t. Right? I is our symbol for current. Right? Q is our lowercase q is our symbol for charge, not to be confused with Q for heat. So we'll want to make sure we keep that straight. I do want to jump to the reference sheet. Yeah, they also use a lowercase q, but notice they define it up here. Q is heat, Q is charge. So make sure you can keep those straight. And then T obviously is time. Now these are the units that they're measured in. An amp or amperes, that's the unit for measuring current. Right? Charge is measured in coulombs, and then time is going to be measured in seconds in these questions. And so what this sets up for us is that the unit amps is equivalent to the unit coulomb per second. Much like molarity is equivalent to mole per liter, coulomb is equivalent to, amps is equivalent to coulomb per second, right? Nice thing for you is that you don't have to memorize those units because those are one of the only ones that are provided on your formula sheet. Do you guys see they say amperes, coulombs, and seconds? So they actually tell you what those particular things are measured in for that equation. So that's a nice thing to help you out, right? Then sometimes we're going to be using this thing called Faraday's constant, right? Faraday's constant now is going to relate charge to the thing that's going to be moving from these chemical reactions. And that is electrons. Electrons carry a charge, and through redox reactions, they're going to be moving, and therefore they are going to be able to create an electrical current. Moving charges is electricity, right? But what I do want to cross out here is that this is a rounded off version that was on the old formula sheet. College Board is now using a more exact version of Faraday's constant, which is 96,485 coulombs per mole of electrons. So if a mole of electrons moves past a point, that means 96,485 coulombs moved past that point. Yes? All right, Faraday's constant, also on your formula sheet. It is, why do you keep doing that? Over here, Faraday's constant, 96485 coulombs per mole of electrons. Yeah, so nothing we have to memorize at this point or commit to memory. Yeah. So we can just do some straightforward questions. Go on to the next slide here. That say how much charge passes through a cross-section of a wire that is carrying 0.987 amps of current for 12.3 minutes. Right? So we have an amperage or a current. We have a time. They're asking us for charge. Right? So we're going to go to the next slide where it's all blank for you to actually calculate this question. Right? Looking at this for letter A, I should be able to say that my formula, I equals Q over T, and which letter am I solving for in this case? Q. I'm solving for Q, so I can say Q equals I times T. Correct? It. All right, so remember, I is current, Q is charge, T is time. So plugging that in, 0.987. Now for canceling of units and dimensional analysis, I'm going to revert from the shorter version of the unit of amps to the longer version of the unit of coulombs per second. Remember, an amp is equivalent to a coulomb per second given this equation. And so now when I multiply by my time, 12.3 minutes, what am I going to recognize about this calculation? I have a discrepancy with my time units, right? And which unit should I have it in? It should be in seconds because that's what, but really they're both going to cancel out because our answer is going to be coulombs. So you're just doing a minute-second conversion where 1 minute, 60 seconds. Yes? All right, and I'm going to round that to 3 sig figs given my amperage and my time. So that's going to come to 728 coulombs. So that's how much charge was going past that point, right, for 12.3 minutes. Yeah? Going past a point. That's how much charge had gone by. Yes? All right. All right, so let's go back to question B. So now then, we're going to make the chemistry connection because anything can generate electricity, not necessarily chemical reactions. But let's deal with those chemical reactions now where that charge is going to come from a mole of electrons or from electrons. And that's what they want to know here is how many moles of electrons then were passed through. So what am I going to have to use to figure out if I know the current that was going through the wire? How can I figure out the number of moles that were going through the wire? Faraday's constant, right? That's how you can connect that charge to that idea of electrons. So here, I'm just going to use dimensional analysis. I know that I had 728 coulombs, right? And so Faraday's constant, 96485 coulomb in the denominator per mole of electron in the numerator. Yes? So now you can see my coulombs are canceling, leaving me with moles of electrons. Yeah? All right, so this is going to come out to 7.54 times 10 to the negative third moles of electrons. I put it in scientific notation. You don't have to. Yeah, so not a whole lot of electrons, right? Not considered a pretty high amperage there. All right, so we're going to come back to calculations involving amperage and time and current and moles of electrons actually at the very end. But realize we can use this equation for any electrochemical cell, regardless of if it's a favorable or non-favorable cell, right? But when we talk about it next time, we're going to focus specifically on the unfavorable electrochemical cells. Yeah, but they can just be used in general anytime you're dealing with current, voltage, time, and moles of electrons. Yeah? All right, so here we go. Let's get a background. Let's get back up and talk just about general redox reactions, right? So here, I'm going to have a redox reaction occurring. The net ionic equation, it's solid zinc, that's this little metal strip right here, and aqueous copper 2 plus ions. The copper 2 plus is blue in color, right, which makes it a blue solution. There's a spectator ion in here, probably sulfate, that we don't include in our net ionic equation, right? And so when they're in the same container, in the same beaker, that means that there will be physical collisions between the two reactants. The aqueous copper ions will be physically running into the solid zinc atoms, yes? And by physical contact, there's going to be a direct transfer of electrons. In this case, it is the solid zinc that is giving its electrons to the aqueous copper ion directly, like they physically came into contact with each other to do this. Now, why did the zinc give it to the copper? We're going to talk a little bit more about that, but you guys remember the activity series about who was more reactive, right? In this case, you know, in terms of the switching partners, the zinc is more reactive than the copper. Right, so the zinc is trying to oxidize and lose its electrons. The zinc wants to oxidize greater than the copper wants to stay oxidized, right? So the zinc kind of beats them out. We'll talk a little bit more about that later, but I just wanted to remind you that there was that idea of an activity series, yeah? So going to the next slide then, what ends up happening, this is like the right after the electron transfer, look at what has turned or become of those two atoms or ions, those two species. What happened to the aqueous copper ion? It became solid. And what happened to the solid zinc atom? It became an aqueous ion, right? So that's what's going on in a typical redox reaction, right? Where everything is in the same container, right? In a beaker, you can have two aqueous things where this could be happening, or you can have a solid and an aqueous thing. There's usually going to be some aqueous component to these reactions, but not everything has to be aqueous. You can also sometimes like produce gaseous products, or you might have some liquids involved. Some other things. Guys, I just made solid copper, right? And it's kind of getting incorporated somewhat into this crystal lattice structure of the zinc, right? Remember, think of different types of solids and the unit cells, yes, that they could have. So this atom can occupy a spot in the crystal lattice. Visually, if I'm looking at this bar, then what will I start to see? I'm going to start seeing that bronzy orange copper color, right? All the way around, because I'm removing these silvery solid zinc atoms and replacing them with these bronzy solid copper atoms, right? So that is a common thing that you will see, is you will actually see this entire metal rod get coated in solid copper, right? And if it gets completely coated, that can actually stop the reaction if the aqueous copper ions can't reach the solid zinc atoms anymore. That's part of the purpose of coating different metals. Like I'm trying to think of the example, like galvanized steel, isn't that like coated in something else? Like that's kind of the goal, is they're trying to coat the really reactive thing underneath with something that's not reactive on the surface, right? That's kind of what they've done in that case. So now I've coated this with solid copper, and the copper ions are not reacting with the solid copper. Yeah. Okay, let's see. If I were looking at law of conservation of mass, law of conservation of mass is followed here. Because whether it's a copper ion or whether it's a copper atom, the mass is still the same. Remember, electrons have negligible mass when you're considering atoms. Yes? However, you can most definitely say that the solid zinc metal strip is losing mass from the zinc. It is now comprised of less solid zinc. Therefore, the zinc's mass would be less. Just as you could say that the mass of the solid copper is increasing, right? So we'll come back to that again later. Okay, so that is a general setup for a redox reaction. Just another quick note. Right now, this electron transfer, looking at these charges, this corresponds to 2 electrons exactly. But that may not always be the case. Let's pretend here. I'm going to write just a little scenario. You can say pretend that this is a copper atom, and now I have silver ions floating around here, right? And they're going to run into each other. The silver ions are going to run into the copper atom. Well, given this half reaction, how many electrons is that copper atom maybe going to want to give up if this is a favorable reaction? It's going to want to give up 2, right? But how many does the silver need to become solid? Only 1. So the solution is the copper gives an electron to each silver ion. So sometimes you need multiple ions to collide with the copper in order to complete the electron transfer. That's the symbol for electron. And then yes, you would make an aqueous copper ion. Yes, you would make 2 solid silver atoms, right, in that reaction. So you do have to pay attention to the electron ratios, right? That's just balancing the redox reaction. But up here, we can see from this one, everything was a 1-to-1 ratio. Right here it would be a 1-to-2 ratio, solid copper to silver. P.S. I'm pretty sure this is an unfavorable redox reaction, would not happen, right? I think the copper is lower on the activity series than silver. So, okay. So how are we going to utilize this for chemistry? Yes, to use this chemical reaction to now generate electricity. Well, the idea is the electrons were moving. But in this case, since they were moving via direct contact, we had very little opportunity to utilize those moving electrons. But what if we could segregate these reactions into 2 halves? And we could provide a pathway via which the electrons could move so that we would still allow a transfer of electrons, but we're kind of intercepting them in the middle. Yes? That's what we're doing with these redox reactions. We are segregating the reactions, the half reactions, and forcing the electron transfer through something of our choosing, like a wire connected to a light bulb or something like that. So we're just harnessing the movement of the electrons, and we're delaying that transfer from one reactant to the other by forcing them through this wire. And that's where we're getting started with here. Oh wait, this is just writing a reaction, isn't it? Well, that's boring. Okay, so we're going to do that here in just a minute with our voltaic cell, but one last slide, sorry. When you're writing these reactions, again, always keep an eye out for the spectator ion. In this particular reaction, we've got copper and silver fluoride. So I'm not going to write out the full balanced equation, but it would make sense that if this reaction occurs, aren't the metals the ones that are switching places? So the solid copper is going to end up in the compound copper fluoride, and the silver is going to kick out and become solid silver. The point that I'm getting at is the fluoride in this case is the spectator ion. Fluoride is spectator, and I would say in compounds always. And these are aqueous salts, which means it always dissociates, so your F minus is going to be a spectator, right? It's going to appear on both sides. It can cancel out, right? So our job then is just writing these half reactions, yes? So here we go. I'm going to start with solid copper, right? Solid copper is one of our reactants. And then aqueous silver is our other reactant. Okay. So this solid copper, it's going to turn into a copper ion. Now, I'm going to tell you the charge of this ion because copper can take multiple charges. You would have information to know which charge the copper would turn into, but this solid copper is going to make copper 2+. That is the most common charge of copper. And then the silver ion is going to turn into solid silver. That's a very common redox reaction where metals displace each other. One goes from solid to aqueous, the other one goes from aqueous to solid. So now it's our job to balance these half reactions. Like we did yesterday. Step 1, balance the non-HO atoms, right? And hey, guess what? They're both balanced. One copper, one silver on each side. Okay. Step number 2, balance the oxygens with water. I see no oxygens. Skip. Step number 3, balance the hydrogens with hydrogen ions, no hydrogens. So last step, balance the charge with electrons, right? And so that's what we need to do here. The more positive side in that copper half reaction is the product side. It's going to be off by 2. So I'm going to add 2 electrons. And then down here, the silver's off by 1. So I'm going to add an electron right there. Hey, we just balanced 2 half reactions. So last step, need to put them together. But what's going to happen before I put them together? I got to balance the electrons. What's my least common multiple here? 2. It's going to be 2. All I need to do is just double this reaction. So I'm going to rewrite it over here because I think we can handle this. So 2 silver ions plus 2 electrons yields 2 silver atoms, right? Which I should put solid in here. You'll see that I tend to indicate on ElectroChem, I indicate solids, liquids, and gases, but I leave the aqueous things alone. So, because they have charges. If they have charges, they have to be aqueous. Like, that's it. They can't have charges and not be aqueous. So then last step is add it all together. And when I add it together, I will end up with solid copper plus 2 aqueous silver ions yields copper ions plus 2 silver atoms, because the only thing canceling out were my electrons. So that's just how you write a balanced redox reaction. Hey, for practice, let's identify these as oxidation or reduction. Was the copper oxidized or reduced? The electrons are a product. It is oxidized. Here, the electrons are a reactant. Therefore, it is reduced. So that was our oxidation and our reduction half reactions. Okay. So now, I was one slide too early. We're getting into our first of electrochemical cells. So here we go. A galvanic cell. A galvanic cell is also known as a voltaic cell. So those are synonyms. You should be able to use either one. And it says a device that transfers electrons from one reactant to another through a pathway. That's the key. We are now controlling the electron flow. We're not going to let them handle it by themselves. We're going to put them in separate bedrooms and be like, we will take and deliver the electrons to the other room. Don't you worry about it, right? And by doing that, we're going to be able to harness that movement in the form of electricity. Like it's going to generate electricity for us. Okay? So this is as opposed to a direct transfer. For me, this is another big thing. Voltaic cells, galvanic cells, they are always spontaneous, or we should probably use the better word of favorable. That means they have positive delta G's, or you could say their delta G, negative delta G's, their delta G is less than 0, right? And so we're going to convert chemical energy into electrical energy. Yay. All right, let's take a look at one of these galvanic cells. Here we go. Oh, it is right there. All right, so here's a galvanic cell. And this is the redox reaction that it is showing. All right, a galvanic cell has two separate compartments, right? Each compartment houses its own half reaction. So here is what appears to be one beaker. Here is a second beaker. Those are your two half cells, is what we would call them, right? This half cell contains a solid strip of metal that you must always have. You must have an electrode, a solid electrode in each cell, and an electrode is simply a metal strip, right? So here I have a zinc electrode and here I have a copper electrode because those are your solid metal strips, right? To further distinguish between the two, we can then call them an anode or a cathode, right? The name that it's called depends on which type of half reaction is occurring in that cell. Is it an oxidation or a reduction half reaction? So here's a cute little trick to remember which one's which, and that is anox, red cat. Anox, red cat. At the anode half cell or electrode, that is where oxidation is occurring. And in the cathode half reaction, cat, reduction is occurring. Right? So you see it does say that at the bottom here, that this is your oxidation half reaction, this is your reduction half reaction. And they show those half reactions right above. Okay? Now, what are these electrodes made of? The metal strips. Why zinc, why copper? Well, looking at your half reactions, if your half reaction contains a metal, then that's what you would use. It doesn't matter if that metal is a reactant or a product. This particular half reaction had solid zinc, so that's why the anode is comprised of solid zinc. This half reaction was comprised of solid copper. That's why that electrode was made of solid copper. But what happens if your half reaction does not contain a solid metal? Well, then you're allowed to use substitutes, all right? And so you can substitute PT. What element is PT? It's platinum. Platinum or solid carbon. You can use solid carbon or graphite as well. And so you can substitute these for electrodes when your half reaction does not contain a solid. Why these two? They are relatively inert, meaning they will not react with the other stuff going on with your half reactions, right? So sometimes you'll see these made of platinum or copper. I feel like we use copper a little more recently because it's cheaper, platinum a little more expensive, but historically we use platinum most of the time, right, for inert electrodes. Okay. All right, so here you need to also in your beaker have any other reactants or products from your half reaction. So we've already taken care of the solid zinc with the solid zinc anode. But my product is aqueous zinc ions. So that means I need a solution of zinc 2+ ions. Here it appears I've used zinc sulfate, right? So I just have a beaker filled with zinc sulfate and then I put a zinc metal strip sitting in it, right? So that's prepping that half cell. Over here, I've already taken care of my solid copper. Now I need some copper 2+ ions. So once again, given this right here, that was probably copper 2 sulfate that's dissociated in an aqueous solution, right? And again, copper's that pretty blue color. So I just have a beaker filled with some blue copper 2 sulfate, and then I stuck a strip of solid copper in it, right? All right, so next thing that you're going to need a salt bridge. A salt bridge is a semi-porous structure. There's different ways that you can do this. We're going to talk a lot more about the salt bridge on a later slide, but it is necessary for moving charged ions from one half cell to the other. We'll come back to that. And then lastly on here, you see this is supposed to represent a wire, right? Up here, coming out of the anode, going across into the cathode. Now, in the middle of this wire, I've set up a light bulb. You can also put a voltmeter that would be measuring the voltage as the electrons are flowing through that wire, right? Okay, so here is the general idea. Well, I guess we'll get to that in a minute. Yeah, let me just make sure I got everything that I want to say. All right, this is a battery, by the way. Oh, and that's what I meant to write back here on this slide, that this is a battery. Yes, because this chemical reaction is going to favorably happen. I don't have to do anything. I just have to get the reactants there. And now electrons are going to flow on their own. And so it's going to generate electricity, right? A voltage. So when does the battery die? The battery dies when one of your reactants is gone. It's like a limiting reactant question. Yes? So either when my solid zinc is gone, this entire metal strip is gone and basically dissolved, if you will, or I run out of copper 2+ ions, right? When one of those is gone, that's when your battery is dead because there will be no more electron flow. Okay. All right. Okay. So let's go to the next slide. Let's get a little bit more detail. What's actually happening, right? By connecting these with a wire, we are setting up a scenario where the copper solid over here is still pulling the electrons. It's like calling like, hey, I really want you. Think of like telephone. Yeah, we've got this little wire that the copper's like, send me those electrons. And it's traveling through the wire over to the zinc, right? There is still think of rolling downhill need for this zinc to give electrons to the wire, travel through the wire, and then deliver them to the copper, right? That's where your electron transfer is occurring, is through the wire. And as a result, every time electrons get pulled out of here, they had to come from somewhere. So there used to be a solid zinc atom right here. But every time, whenever this solid zinc electrode lost 2 electrons, it turned from solid into an aqueous ion. And it basically falls off of the anode and is now floating around as a dissolved ion in solution, right? And then likewise over here, once these 2 electrons get here, now you have 2 extra electrons. So when a copper 2+ ion bumps into it, guess what? It takes those 2 extra electrons, right? And when it takes those 2 extra electrons, now, I don't even need to put a dotted line, now it forms a solid copper atom. And so that's how the electron transfer happens, is through this wire. And we'll talk a little bit more with voltage, why it goes through the wire, but that's what's happening. Solid zinc drops off 2 electrons into the wire. As a result, one of its atoms becomes aqueous to zinc 2+ ion, right? It lost 2 electrons. And then when the 2 electrons get over here to the cathode, the solid copper, and a copper 2+ ion bumps into it, it takes those 2 extra electrons and solidifies, essentially. It precipitates, if you will.
You said that one of the reactants are used up, it's like one big reactant.
Yes.
How does rechargeable batteries work?
So you force the reaction the other way.
Okay.
So you force the copper to give the electrons back.
Okay.
Yeah, which we'll talk about those too. That's an electrolytic cell. Yeah. Okay. So some other things to consider then. If this is my electrode, over time, what is happening to the mass of the anode? This thing is losing mass. However, in that entire beaker, why would I say that entire beaker is not losing mass? Because it's still there, but now it's there as a dissolved ion. Can I tell you the most frequently given answer to that question? Why is the anode losing mass? They say it's losing mass because it's losing electrons. Why is that like really not a good thing to say? Electrons don't have mass, right? This is losing mass because it lost a solid zinc atom, but overall mass is conserved because that solid zinc atom just became an aqueous zinc ion, which shares the same mass. So in the beaker, or in the whole cell, there's been no change in mass. I'm just referring specifically to the anode that's losing mass. Okay? All right, so then over here, my cathode, over time, what's happening to its mass? It's gaining mass. And why is it gaining mass? It's gaining a solid copper atom, right? Not because it's gaining electrons. Remember, the transfer of electrons does not change mass. It's only gaining or losing solid atoms that are changing the mass of the electrodes, right? But once again, what is true for the entire either half cell or entire cell? Total mass is conserved. Although I generated this solid copper atom, I just replaced an aqueous copper ion that shared the same mass, right? So total mass is conserved. Next thing, what happens if your electrode is platinum? Let's say I had a platinum anode. What would happen to its mass? Stay the same. It's going to stay the same. It's neither a reactant nor a product in the redox reaction. All it is just a surface through which electrons can transfer. Something's going to run into it, drop off electrons. Those electrons are then going to move up into the wire over to the cathode, right? It is simply a place for electron transfers because with those delocalized electrons in metals are really good at shuffling electrons around, right? So if it's the anode, it will not gain mass. It will stay constant. What if it's the cathode? Look at this example. What if this cathode was platinum? Nobody wants to take a guess? Okay, I'm going to say it depends. It depends on what the product is of that half reaction. In this example, it would increase because I would have the solid platinum, but then wouldn't I be coating it with copper? Yeah? So if I'm making solid copper on top of the platinum, the mass would go up. But if my product, right, after it drops off the electrons, if my product was either something aqueous or something gaseous or something liquid, then the mass would stay the same, right? So remember, this is just a place to deliver the electrons, and it matters what we're delivering it to. If we deliver it to something that then turns solid, then yes, its mass will increase. But if we deliver it to something that remains aqueous, gaseous, or liquid, then the mass would stay the same, right? Other things to consider. Hey, let's say one of the products of my redox reaction is a gas, right? What do you think that means for the total mass of your cell? If one of my products is a gas. It's probably going to be less unless you're trapping that gas, right? So if you're making a gas and it's bubbling out of your cell, then overall you will see a drop in mass of the cell. Likewise, I saw a voltaic cell on an FRQ a couple years ago that I never heard of. It was called an open air cell. And part of it actually, you had to bubble a gas across your electrode, right? Because the gas was a reactant in that case. And so in that case, the mass of the electrode increased because you were putting the gas into it that was then causing stuff to get made, right? I don't know. It was interesting the way that it was set up. So kind of look at your overall reaction, right? If you are putting in gases and then getting solid stuff, your mass is going to go up. But if you have solid and aqueous things and then you're making a gas that's going to dissipate, then the mass is going to go down, right? That's what you should think about. For the entire cell is what I'm talking about here, not necessarily just a half cell. Okay. All right, so let's maybe wrap up today by talking about that salt bridge and the super important function of the salt bridge, okay? That picture was a salt bridge that we call a U-tube way before YouTube ever existed. Yeah, like I think YouTube stole it from, okay, anyhow. That's a really common one, but there's other ways to do this. I actually can get out an example after spring break. I didn't want to do it today and have to clean it up, but after spring break, I'll get out and set up one of these for you where I use just a beaker, but then I have this little ceramic porous kind of beaker where it's that ceramic porous thing that's acting like the salt bridge. I've also seen them with gels where they actually have like one single compartment that they slide this thing down the middle to separate, that acts as the salt bridge. So, I mean, there's a variety. We're going to use filter paper as our salt bridge for our lab. There's a lot of different things can serve as a salt bridge, but the old school ones were U-tubes. These are common ions that end up in your salt bridge. You do need soluble ions in there, right? The ions that go into your salt bridge cannot play a role in the redox reaction. They cannot interfere with it, mess with it. They should be completely inert and not part of the reaction at all, right? So do not play a role. The ions from the salt bridge must not react with ions in the electrolytic solution to form a precipitate. So again, you want them doing nothing except being there. So you do have to carefully select your ions, right? And here, for me, is the main thing that College Board focuses on. And that's the purpose. Why do we have to have it? You need the salt bridge to maintain the neutrality of the cell. Without the salt bridge, you're taking a bunch of electrons and you're moving them to one side, right? So you're going to have a buildup of negative charge on one side, and you're going to have a buildup of positive charge on the other side. That's bad if the electrons want to go downhill, right? Because don't the electrons, they go to the cathode, but if I'm building up a negative charge there, that can eventually start repelling the electrons away. That's not good. So we use the salt bridge to replace ions of different charges to keep both sides neutral so that we don't have a buildup of negative on the cathode side and a buildup of positive on the anode side, right? That's the purpose of the salt bridge. I think most important point on this slide. So yeah, if the solutions don't remain neutral, the reaction stops. As I said, the cathode half cell will start repelling the electrons away if they build up that negative charge, right? All right, so just looking at two pictures here, how do you know which way they go? Well, I came up with a really easy way. Anions. Anions have what charge? Negative. Anions get delivered to the anode, right? AA. Anions get delivered to the anode. If you think about it, the electrons are going to the cathode, so the cathode's getting a buildup of negative charge, which means your anode's getting a buildup of positive charge. You need to send negative charges over there to neutralize, right, and get back to zero. So you can see in this example, it looks like it's the sulfates, the negative sulfates that are getting delivered to the anode. Yes. And then, next slide. The cations get delivered to the cathode. Cations to cathode. Yay! Because once again, the cathode is building up a negative charge once they accept all of those electrons. And notice here, they actually can start pulling zinc ions. So even though it looks like it's delivering sodium ions to start, the zinc ions will be sucked up into your salt bridge should they need to be delivered there to maintain the neutrality. If you've exhausted all of your sodiums, then you might actually start pulling zincs as well. That could deplete your battery faster if you don't have a high enough concentration of sodium ions. Well, again, depending on the... Yeah, actually, in the case of the porous one that I use, they don't use a salt because they just let the positive ions move there. I'd have to research more. Your book has a chapter more specifically on batteries and different types of batteries, so maybe you can look there to know exactly what they're doing with their salt bridge, because I actually don't know what they're doing. Yeah. All right, and then here we're just talking about changes in mass. I always encourage you to look at your half reactions. Right? If you're making something solid, then the mass of that half cell should be going up, right? If you're using up something solid, then the mass of that half cell should be going down, or at least the mass of that anode, if those things are comprising the anode and the cathode. They should be changing. You can also think about whether a gas is being incorporated into a cell, or if a gas is being released from a cell. That could affect the overall mass of the cell itself, or the half cell. Here I was talking of specifically losing mass. It's the actual anode metal strip that's losing mass. But remember, we also said that total there would be a conservation of mass because that solid atom is now just an aqueous ion with the same mass, right? And what did I say? you should never use as an explanation for why anything in an electrochemical cell would gain or lose mass. What is never the answer? Electrons. Electrons have no measurable mass that we care about. So mass will never change because you've lost electrons or you've gained electrons. Always go back to the equations, the actual equations, and look intelligently about what things are being used up, what things are getting made, what's going in, what's coming out, right? What's on the metal thing? Is more of that metal getting made, or is more of that metal getting used up, right? That's what you should use to explain changes in mass. Yeah. All right, and that was the salt bridge. We talked about that. You can remember AA, anions to anode. CC, cations to cathode. That's in the salt bridge. That was a free response question a few years ago. They had a zoomed in version of a salt bridge, and they're like, hey, show which way the ions are moving in the salt bridge. And you just had to draw like a K plus and make sure it was pointing towards the cathode side, because cations go to the cathode. And then I think it was a nitrate. You had to draw a nitrate ion and have an arrow pointing towards the anode side. That's it. Yeah? Okay. So with that, that was probably a little more than 2 minutes, but I think it's okay. So we're coming back to Graham's question. And that is, why are these electrons moving in the first place? Right? So I kind of gave you a sneak peek of this. So guys, I'm going to be honest. Slides 14 to 20 are really just about trying to help you understand what voltage is measuring. Okay? So to do this, we are going to use an analogy of a boulder and a cliff. Right? The boulder is going to represent the electrons, and then the top and the bottom of the cliff is going to represent the different half cells, anode or cathode. Right? So here we go. Why do they move? Guys, this is the answer. The potential energy for the electrons is higher at the anode than it is at the cathode, and everything moves to achieve a lower potential energy state. Right? Like, that's a natural thing. Again, that's how gravity works. Everything's moving to lower potential energy. But let's try to make this more real for you guys by making an analogy to a cliff and a rock. So here we go. We're starting really basic here. I've got a boulder. I got a rock here, and I want to lift this rock to the top of the cliff. It's going to take some work to do that. This is the work equation. You're not tested on it. But let's say, given the force I have to apply and the distance I have to move this rock, let's just say that this rock required 12 joules to lift. Right? And work is measured in joules, meaning it is a form of energy, right? Energy transfer. Just like heat is energy transfer, work is energy transfer as well. Okay? All right, so yeah, I'm pretty strong. I'm going to lift this boulder up to the top of the cliff. All right. Now, let's think of it the other way. Now this boulder, this rock, is at the top of the cliff, right? And what do we know about the first law of thermodynamics? Energy is conserved, neither created nor destroyed, right? Energy conserved. So this 12 joules of work that I just did, where did it go? And the answer is, it is now stored in the rock as potential energy. This rock now possesses more potential energy than it did when it was at the bottom of the cliff, right? That's something we might have talked about in like a physical science class, right? The higher off the ground you are, the more potential energy you have. So we can now say that the change in potential energy of this rock is going to be equal to 12 joules, because I needed 12 joules to get it up there, so that means that 12 joules is now stored in potential energy in the rock. Yes? So again, work transferred the energy. So the idea now is, if this rock were to fall again, how much energy would it release? 12 joules. If it took 12 joules to get it up, guess what? It's going to give up 12 joules when it goes back down. In that case, it is going to go out in the form of kinetic energy, right? I had to do work to get it up, but it's going to go back in kinetic energy whenever it falls. So we're kind of talking about the work we needed to get it up, because then that helps us better understand the energy that we would derive by letting it fall. That's what this whole thing has done. So this change in potential energy can be related now to this idea of voltage. We can talk about electrical potential energy and this thing called potential difference, right? Which is analogous to voltage. See, that's a V for voltage. When you talk about a battery, right? This is what, a AA battery, and this is, I think, 1.5 volts. Yeah? Yes, this is 1.5 volts. What I am telling you is how much energy you can get per charge of stuff moving, which in this case is going to be electrons. It's energy per charge. And you can think of it as the electrons falling off of a cliff. How much energy would they get? But then you're also dividing it by the charge of those electrons. So this equation here, don't panic. You are not using this. We're not using this equation at all. I'm just trying to give you the idea behind what voltage is measuring. So when I say 1.5 volts, that means I would get 1.5 joules of energy for every 1 coulomb of electrons that were flowing from the anode to the cathode, going downhill, falling off the cliff, right? That's what it's telling me. So all this does right here is to make our lives easier so that we can relate voltage and then this potential energy change, is it's just saying, well, if one electron has this charge, then this many electrons is 1 coulomb. And now that means my denominator is 1. Let's just make our lives easier and talk in terms of 1 coulomb. You're never going to need that 6.25 number, don't panic. I was just trying to simplify this analogy for us. So let's apply this now to a galvanic cell. Here we go. Guys, this is our battery. Think of that picture of a galvanic cell that we just looked at, the one that had the salt bridge, yeah? And imagine you took that cell, it was right here, this one, and imagine you turned it on its side. That's kind of what I'm doing here. That there's your anode, there's your cathode, and here's your wire. I guess maybe I turned it this way, yeah? Here's your wire, and that says 12 volts just because that's where a battery is. But that's kind of what we're trying to simulate here. Now we're thinking of the galvanic cell as a cliff, where the anode is the top of the cliff and the cathode is the bottom of the cliff, right? So let's switch this around. Here is 1 coulomb's worth of electrons, 6.25 times 10 to the 18th, right? If I want to get all of these electrons to the top of the cliff, right, it's going to take me, well, here, let's do it this way. .25 times 10 to the 18th electrons, that is equivalent to 1 coulomb's worth of charge. And in this picture, it tells me that my battery is 12 volts. So if I think of voltage as change in potential energy per charge, what would my change in potential energy have to be in that equation? X has to be 12 joules. Right? I'm using 12 to match the previous example. But that's my 12 volts. That's what it's telling me. If I had 1 coulomb's worth of electrons, that it would take 12, or I would get 12 joules of energy when it falls. It would take 12 joules of energy to get it up to the top of the cliff, right? That's just a change in sign, positive or negative, depending on if you're going up or down the cliff, right? That's what I'm measuring with 12 volts. I'm telling you per coulomb, how much energy can I get? 1.5 volts means I get 1.5 joules of energy per coulomb of charge. Yeah? And so this slide is just showing the opposite, it going down. If it's going down, that means now I'm getting the 12 joules. I don't have to put the 12 joules in. But I'm not going to write anything else for that. It's the same idea. But here's what I do want to point out. Let's try a for instance. What if my boulder, my rock, wasn't 1 coulomb worth of electrons? What if it was 2 coulombs worth of electrons, right? But yet this is still a 12 volt battery. So if this is still a 12 volt battery, but I switch this now to be 2 coulombs worth of electrons, how much energy would I get when that 2 coulombs worth of electrons fall? 24 joules, right? So just kind of putting this out here. This would be similar to saying my rock is twice as large, because I have twice as much charge, that means I'd have to have twice as many electrons. But if my rock is twice as large, that means it's going to take twice as much energy to either get it to the top, or I'm going to get twice as much energy if it falls back to the ground. But yet, what happened to my voltage? It stayed the same. Voltage is a constant ratio. So this is going to come into play in a couple of slides because we're going to start messing with half reactions. And you guys remember how for delta H, if you flipped the equation, you could flip the sign of the delta H? Well, guess what? If we flip a half reaction, we're going to be able to flip the sign associated with the voltage. But here's where things are going to be different. When I doubled an equation, I could double its delta H. But when I double a half reaction, I cannot double its voltage. Because doubling the half reaction is like doubling your number of coulombs, which means you double the energy, but the ratio itself stays the same. Yeah? So you will never double, triple, half a voltage. Voltages are constant. All you can do is make them positive or negative depending on if the electrons are falling down the cliff or getting pulled up the cliff. Right? Okay, so this slide, I'm not reading you anything. It summarizes everything that we just talked about. So voltage, energy per unit charge. That's really our main takeaway here. Try to give you some background on where it comes from. So now let's get into what we need to know. Potential difference, this delta V, right, has a lot of different names. EMF is one you might be familiar with. Electromotive force, that like hit the EMP thing to blow like the EMF signal and destroy all of the electronic devices in whatever universe you're in. Okay, right? Same idea that we're talking about here. It's the force that causes the electrons to move, right? It's kind of talking about how steep that cliff is. I should say hill, not cliff. If I throw the word standard in front, just means it's standard conditions, right? Now, these are the two that we most frequently use. This is what College Board has on their exam. Capital E representing energy, because that's what voltage relates to, energy per charge. Cell is talking about the electrochemical cell. Right now, we've only talked about galvanic or voltaic cells, and we call it cell potential, right? It's the cell potential. It's the potential energy that you can get out of that battery, right, in that cell. If we put the little degree sign, it just means we're at standard conditions. So it means those solutions have to be 1 molar. If you're a bubbling gas, it has to be 1 atmosphere. Temperature has to be 25 degrees Celsius, yeah? Those are your standard conditions. I'll also talk about cell voltage, the voltage of the cell, right? So like that's your batteries. It's a 12-volt battery. It's a 12-volt cell, yeah, cell voltage. And units for all of these are volts, right? Okay, the next slide reminds us about standard conditions. We know those, yeah? Okay, means everything reactants and products have to be in those conditions. So here we go. If I want to know what the cell potential is, if I have made a battery, which you guys are going to get to do with galvanic cells, you're going to make it yourself, right? And I want to know what voltage it's going to produce. What we're going to do is we're going to look individually at the half reactions and what voltage each half reaction could produce, right? Most of these numbers are already provided for us in the form of reduction potentials. I don't know why they picked reduction, but they took every possible half reaction that you could have, and they just reported them all as reduction potentials. So for that half reaction, what would be the voltage if it was a reduction, right, that would be generated? And by looking at both the reduction and the oxidation half reactions, we will then be able to determine the cell potential for the entire galvanic cell, right? So here's an example of a standard reduction potential. This is the reduction of the copper 2+ ion. And you see here standard E naught with RED, that's reduction. If I were to flip this, what's happening here? Solid copper yields copper 2+ plus 2 electrons. That's no longer a reduction. That's an oxidation now, right? And so that means I have a standard oxidation potential, but they don't publish those anywhere because everybody knows that you can just flip the reduction to make it an oxidation. So instead of making it confusing to know which one you have, everything published is reduction potentials, and then you can manipulate them to make them oxidations. And so what do I do here? Well, if I flip the half reaction, flip the sign. It's the difference between going up the cliff or down the cliff, right? So this is a negative 0.34 volts, right? So I'm just going to say flip sign. That's what I need to do if I flip the half reaction. Okay, so let's play devil's advocate here. 2 solid copper atoms yields 2 copper 2 plus ions and 4 electrons. Okay, first thing, that's still an oxidation. We're losing electrons as products. But my oxidation potential still a negative 0.34. Why is that? Because it's a constant ratio. Even though you could argue that my electron boulder is twice as big because it went from 2 electrons to 4 electrons, remember, it's a ratio of energy to charge. Twice as much charge means twice as much energy, and they cancel each other out, right? The voltage stays the same. So make sure we put a note of that same number, right? Even when you multiply a half reaction, leave the number the same. The only thing you can do to a voltage is make it positive or negative. Okay? All right. So here's a sample of a table of reduction potentials. So you see all of the reduction reactions on the left. You see all of the reduction potentials on the left, right? Now, where exactly did these numbers come from that this is considered like a table that gets published? Well, it all starts in the middle. This is the reduction of the hydrogen ion. And if you notice, its voltage is set at 0. Because this is the half cell by which everything else is compared. So we set up this hydrogen half cell, and then we set up something else and we measured the voltage. And then we had a hydrogen half cell, we set up a different thing, we measured the voltage. Everything is in comparison to whether or not it will oxidize the hydrogen gas or whether or not it will reduce the hydrogen ions. It's trying to figure out those other things. Are they higher, a cliff higher compared to the hydrogen? Or is the hydrogen the top of the cliff and the other thing is the bottom, right? That's what we're trying to figure out, and that's the difference between these positive and these negative charges. Excuse me, I say charges, voltages. Voltages, okay? When your voltage is positive, that is the favorable reaction, meaning these are reductions. This thing is favorable to be reduced against hydrogen, right? So silver will reduce, hydrogen will oxidize, right? Iron 3+ will reduce, hydrogen gas will oxidize, right? That's what these are measuring. And the bigger the number is, the more favorable it is. The more likely it is to reduce compared to other things. These things down here are unfavorable. They're unfavorable to reduce. But what happens when I flip them? What happens to their voltage? They change the sign. And when I flip a reduction, it becomes an oxidation. So even though these are unfavorable to reduce, that means they're favorable to oxidize, right? So in this case, these guys would oxidize while the hydrogen ion reduces, right? And so this hydrogen guy right here in the middle, it has a name. It's called a She, a standard hydrogen electrode. I'm going to show you a picture of a She here, because it has a gas. I think it's interesting for you guys to see that. So if you remember, the half reaction had hydrogen ions, and it also had hydrogen gas. Number one, that meant that there was no metal in this half reaction. Hence why this little piece right here is likely platinum, right? You see the wire, it just extends down lower. Your electrode doesn't have to be a giant long strip, even though it usually is. It can just be a little square, that's fine. You just need a place for that electron transfer to occur, okay? And then, depending on what's over here, one of two things can happen. Either the hydrogen ion is picking up electrons and turning into hydrogen gas, or the hydrogen gas is losing electrons. What happens is you have a pipe here, tubing, that's pushing hydrogen gas, pumping it into this tube so that it's bubbling over that metal platinum plate. The hydrogen gas has to come into contact with the platinum plate either to drop off electrons, or the hydrogen ions have to bump into that platinum plate to pick up electrons. And the answer for if it's going to drop off or pick up is entirely dependent on what's over here, right? You have to figure out, here's the hydrogen, is copper at the top of this cliff or is copper at the bottom of this cliff? And given the direction of the electron flow, it looks like it's at the bottom. So in this case, this was our anode. The hydrogen was losing. The copper was the cathode. It was gaining. But I could have switched this with something else, and it would have been the other way. This could have been higher, and the electrons could have flown the other direction. And this would have been the cathode, and that would have been the anode. That's kind of what they were figuring out. Everything was in comparison to hydrogen, right? The She. So that's where all of these numbers come from, and that is the table that you guys picked up today. This used to be provided by College Board with your equation and formula sheet, but it's not there anymore. I'll tell you why. The one on the back is just another one from the internet. If I give you stuff, I don't know if you'll need them or not, but you have them here. Guys, can you wait a second, please? Stop with the papers. The reason they don't give you this massive table anymore is because if you need standard reduction potentials, they will give you the half reaction and the reduction potentials within the question. So they're not going to make you go hunt through this giant table. They're going to give you anywhere from 2 to 5 half reactions and reduction potentials to then do something with. So that's why you don't need them anymore. Yes? All right, so last things to talk about, is what we can now say about things relative to each other. I do want to just finish this one slide. The silver ion, this is a reduction half reaction. It has the largest positive reduction potential value. That means on this list, it is the most likely to reduce. If I had to pick something that was going to reduce and that was going to oxidize, if they were all together, this one is the most likely to reduce. That means this aluminum 3 plus should be the least likely to reduce. But if the aluminum 3 plus is the least likely to reduce, what do you think that means for the solid aluminum? Most likely to oxidize. You guys have space under the slide to write this, but if I flip this equation and make it solid aluminum, making the aluminum 3 plus and 3 plus electrons, its oxidation potential is positive 1.66 volts, which would by far be the most positive oxidation potential if I were to flip all of these, right? So that's how we're going to decide which things to flip. We want everything to be the most favorable in a galvanic cell. And our rule of thumb is the most positive reduction potentials we leave alone, because those are the most favorable ones to reduce. Thank you. We'll pick up tomorrow. So just to recap, because I want to make sure we're all on the same page, right? We were talking about the concept behind voltage. Voltage is a ratio. Energy per charge. Right? Energy per charge. And remember that ratio was important because it was constant. It didn't matter if you double or triple the number of electrons being lost or gained. Since it was a ratio, the amount of energy transferred would have changed accordingly, right? And so that's the idea behind voltage. And so now we've said if I want to know the voltage of an entire galvanic cell, one of these batteries, right? What I can do is I can look individually at the half reactions, the half cells. And I can look at their oxidation and reduction potentials. And by looking at those two, that's going to help me figure out the entire cell potential for the entire galvanic or voltaic cell, right? And so this was a sample list of some reduction half reactions with their standard reduction potentials. Everything is done in relation to the hydrogen cell or the She. I know you guys have this. I'm just reiterating. Where one of our cells was hydrogen gas and aqueous hydrogen ions. And then depending on what the other cell was, that determined which way the electrons were going, because that determined which way was downhill. right? And that's why some of these are positive and some of them are negative. The ones that were positive, those are reductions, right? That means the reduction half reaction was favorable. And so that means they were pulling the electrons away from the She, right? But down here, these were negative. That meant that the reduction was unfavorable, right? It was an unfavorable reduction. But if the reduction is unfavorable, then what's true about the oxidation? Favorable, right? If it's unfavorable one way, it's favorable the other. And so if these guys were favorable oxidations, that means they were giving their electrons to the She, right? So that's kind of where everything is measured in standard of, is according to this hydrogen cell, right? All right, so then from there we could start making statements about what was more or less likely to reduce, what was more or less likely to oxidize, right? And here's the key. It's the positive values. The positive values are the favorable ones. Those are the downhill scenarios, right? And that's why we had said very quickly at the end of class yesterday that it was the silver plus ion that was going to be the most likely to reduce. It was the most likely to reduce because it had the largest positive reduction potential, right? I could then say that the aluminum 3 plus ion would be the least likely to reduce, right? But let's flip this. If this Al3 plus is the least likely to reduce, that means if I reverse this reaction, and you guys should maybe write this under the slide, I would end up with this oxidation half reaction, and I would end up with this oxidation potential, a positive 1.66 volts. That would make this the most positive oxidation potential in the list. If I were to flip all of these, flip all of the signs, this now is the most positive, which is why I say the aluminum is the most likely to oxidize. Most likely to oxidize. Now, it looks like it's a product here. That's because it's a product of the reduction. It's always reactants that are getting oxidized and reduced. So that's why here the reactant silver plus and the reduction half reaction was the most likely to reduce. And here the reactant aluminum solid with the most positive oxidation potential was the most likely to oxidize, right? All right, so how is this, again, our goal? Reason why we're talking about this. We're trying to figure out the voltage of a battery, right? That's what we're trying to figure out here. So what's going to happen is you're going to be given 2 half cells, right? 2 half reactions, and you're going to be given them both as reductions. The problem is 2 reductions does not a battery make. It's peanut butter and jelly. You got to have a reduction, you got to have an oxidation, right? So in order to make this a downhill situation, one of them you're going to have to flip, and you got to pick the right one to flip and make it an oxidation. So how do you know which one to flip? Well, I'm actually going to teach it in terms of which one you know you don't flip. And that is you will not flip the most positive reduction value, right? It is the most positive standard reduction potential. That's the one that stays a reduction, because the most positive reduction potential is the most likely to reduce, correct? And that means it's going to beat out the other guy. Even if the other guy is favorable to reduce, the one that's more positive is the one that's going to win that race, the one that's going to be more likely to pull those electrons away. Yeah? So what that means is the other one is the one that you flip. Yes? All right, so once I've figured out which one to flip, then this is our equation to actually figure out the cell potential. And guess what? I don't like it. It's really messy. I think your textbook presents it in a version of this. The slides get a little better later on, but I want to write here on this slide write the way that I do this. An electrochemical cell is made up of 2 half cells. So if I want to know the full voltage of that entire cell, it is simply going to be the sum of the 2 half cells. It is the sum of the reduction potential and the oxidation potential. Now, why did I cross out that reaction below? Because it's subtraction. And for the most part, I hate subtractions because it matters what order you subtract them in, and I sometimes forget which order to subtract them in, right? Because it matters if your answer is positive or negative when you're talking about voltages, right? So that's why I don't like using the subtraction form of this equation, even though I believe your textbook shows it to you that way, or at least it did in the previous version. You should probably check on this one. Yeah? So this is the version of the equation that I will use, and the slides do have a version of this later on. However, it is not given on your formula sheet, right? You know, I say it's an equation, it's like, it's more of a concept, right? The parts equal the whole. The voltages of the two parts, the reduction part and the oxidation part together equal the voltage for the whole thing. That's what I would think of in terms of calculating cell potentials for voltaic cells. Yeah? All right, so with that, let's take a look at our first example. Okay, here we go. Standard cell potentials. First of all, it asks us for the cell potential. Cell potential is represented by that symbol, E subscript cell. Then it tells us that we have a voltaic cell. That means that overall we need to have a favorable reaction. And if overall we're going to have a favorable reaction, that means that your E cell has to be positive. Just like positive voltages for reduction potentials are favorable, positive voltages for an entire cell, those are favorable as well. Yes? So that's something that we can check at the end, right? This also means that we're going to follow our rule of keep the most positive reduction, because we want the more favorable reduction to be taking place. All right, it tells us that we have nickel at one electrode and copper at the other. In fact, they've given us the half reactions down here dealing with the nickel and the copper. Hey, Mrs. Tate, how did I know that these should be the 2+ ions? And the answer is, well, because those are the half reactions they gave me. Like, that's not anything you would have to determine. They will give you the half reaction for whichever ion charge that they want, right? All right, and so it says, what's that potential? The cells are kept at 25 degrees Celsius and all ions in solution have 1 molar concentrations. Why do you think they told me that?
Just so you know that those aren't missing factors and everything.
Yeah, and what are those things specifically? Standard conditions. They are confirming for me that I am at standard conditions, which means I can actually put my little degree sign here, and that means it's good that there's little degree signs there. Yeah? Because otherwise there would be some other voodoo we'd have to do, which is actually not part of this course anymore. Yeah. You'd have to calculate the standard G and then calculate the non-standard G. Okay. All right, so here we go. Here's our problem. We've got the copper, we've got the nickel. Those are both reductions. One of them's got to be an oxidation, right? If I'm going to make this a battery, one of them has to be an oxidation. So my rule of thumb is I look at the two, and whichever reduction is the most positive, that's the one I keep. So that means right here, this is my most positive reduction. And so that's the one I keep. I'm going to leave that copper 2+ reduction alone. But if I'm leaving that one alone, that means I'm going to have to flip this nickel reduction. The nickel ion is not going to reduce in this case. It is the solid nickel that is going to oxidize. And once I know that it's the solid nickel that's oxidizing, I can just flip the sign of that reduction potential to make it an oxidation potential. And now I can figure out the cell potential. Just adding the two together. That's it. So that's what's happening on the next slide here. Here's their crappy versions of their equations. This is the one that I dislike entirely. The second one's actually not bad. I just think they have extra words when they say anode and cathode. Like, why do I need to label that? I know anox red cat if I need to, but in terms of my math, it is simply the cell potential equals the reduction potential plus the oxidation potential. That's it. All right, so I will do that. Standard cell is equal to, what, we got a positive 0.34 volts. That was my reduction potential on the previous screen up here. And then here's my oxidation potential, right, where I flipped the sign. So plus a positive 0.25 volts. And that means my cell potential total is a positive 0.59 volts. First thing about a question like this. There was an FRQ question a few years back that you had to calculate a cell potential, very similar to this. You did not get the point if you did not show work. For as simple as that addition is, for as easy as it would be to do that in your head, if you did not show the work, you did not get the point. Because they wanted to see exactly what you were adding. They wanted to make sure you didn't copy it off of your neighbor next to you. Right? So as I've said with showing work, I do encourage you to show work for as much as possible, save for, there's never been a point tied for molar mass work. There's never been a point tied for metric conversions. And I don't believe I've ever seen a point tied for showing a Kelvin Celsius conversion, right? Those are like 3 of the big things that I know are not tied to points. But even simple math as like addition, you should still show those, right? Okay, so with that, we can now say, since this has a positive cell potential, that means it is a thermodynamically favored process. This is now a relationship, a statement that we can make going forward. When your cell potential is positive, hey, what would be true of your standard free energy? What would it be? It would be negative, right? Because a negative delta G is thermodynamically favorable, but now a positive cell potential is thermodynamically favorable. Oh, and we just had our MCA. What would be true about K? K would be greater than 1. Now, that does not mean that your battery is at equilibrium. It just means once it got to equilibrium, you would have more products than reactants. Remember, a battery is actually going to be dead at equilibrium because your delta G is 0, and your voltage will be 0 as well. At equilibrium, E and G are 0, right? But we're saying for K, once it gets there, it would be greater than 1. Right? But prior to that, when it's positive and negative, it's favorable. All right, let's look at another example. Determine the value of the standard cell potential. So here they just flat out told us we were dealing with a standard cell potential. For a voltaic cell, that means we're going to keep the most positive reduction. We want a positive answer when we're done, right? Positive E cell. And we're operating on a reaction between silver nitrate and solid nickel. Now, they gave us the half reactions below, but the idea is it's the solid nickel and the silver ion that are going to be flip-flopping. Those are the 2 species involved with the oxidation and the reduction. The nitrate in this case is a spectator ion. Nothing in the nitrate gets oxidized or reduced. It's just hanging out there, which is why you see no nitrate down here, right? All right. So from here, we need to flip one of these, right? And our rule of thumb is which one do we keep? The most positive. And that's this guy right here. More positive. That means that's the more favorable reduction. The more favorable reduction is the one that's always going to occur. Now I say more positive. I don't say largest. It is possible that you could have 2 negative reductions. In which case, leave the more positive one, the one closer to 0 alone, and then the lower one, that's the one that you flip. All right? All right, so this one we will flip, and so that gives us solid nickel, yields nickel 2 plus 2 electrons, and that means our oxidation potential is a positive 0.25 volts. All right, so now that I know which one to flip, what's my last step to figure out the cell potential? Add the reduction in the oxidation potentials. That's it. So that's what we're going to do here. Once again, they've written out the equations, and I don't like that extra stuff. Positive 0.80 volts plus a positive 0.25 volts equals a positive 1.05 volts. Okay. Now, compared to the first example, there was something that happened a little bit different in the second example that I don't know if anybody noticed. Notice anything about those half reactions that I did not address or mention before getting my answer that might have been an issue that you're like, wait a minute, can I do this? What about it? The electrons aren't the same, right? The electrons aren't the same. Well, the answer is, guess what? It doesn't matter. Because remember, since voltage is a ratio, even if I doubled these electrons, do I get to double the voltage? No, because double the charge would just means double the energy, and voltage is energy per charge. It cancels out. The only time I need to worry about equalizing these electrons would be if they want the balanced redox reaction, right? And so that's what I was going to show down here is how would it look if I was trying to get the balanced redox reaction. In that case, I would have doubled that silver half reaction, right? But my reduction potential would have stayed the same at a positive 0.80 volts. And then I would have left that nickel, well, I would have flipped the nickel one, right? I would flip the nickel one to make it an oxidation. And so that means I would have had my oxidation potential of positive 0.25, which means then that my overall balanced equation would have had 2 silver ions plus solid nickel yields a nickel ion plus 2 solid silver atoms. And that's how I would get my cell potential of 0.105 volts. What I wanted to show down here is this is a way that you can do both at the same time, figure out the balanced equation and do the cell potential at the same time. This is a common way to show work for getting cell potentials, especially ones that do require you to get equations and follow the electrons to equalize and write balanced equations. Right? If they just want the cell potential, you can do what we've been doing in blue, but this is a way you might also see in your textbook going forward. It's a nice way to also present the same work, balancing the equation using the half reaction method and calculating the cell potential at the same time. Yeah. All right, so last example. Here we go. This is something you don't need to look at. Okay, here we go. Last example. In a galvanic cell. All right, so that tells us we want our E cell to be positive. Right? Aqueous silver is reduced by an unknown metal. The standard cell potential is found to be 0.47 volts. What is the reduction potential of the unknown metal? All right, so if we think about our equation here, E cell equals E of reduction plus E of oxidation, yeah? All right. So, can we agree that this 0.47, this is our total cell potential? It said the standard cell potential is found to be. But who can tell me why we are not solving for this, even though the question says what is the reduction potential of the unknown metal? What do we see in this question, Claire? We do have a reduction potential, but remember, we are allowed to flip it if we need to. So just because they give me the reduction doesn't mean I have to keep it a reduction. So I guess that's my question. Like, how would I know whether to keep this a reduction or not? How do I know that I'm not solving for this, but I'm actually solving for this? How can I figure that all out reading this question?
Since it's a silver ion, it's the one that's most likely to reduce.
But we don't know what the other thing is. Like, without having a second reduction potential here, how do we know that it's the most positive one, the one that's more likely to reduce? All right. But I mean, even, so like, I could, in theory, make this negative, and then I could have a very large reduction potential. Like, my reduction potential could be like 1.2. I mean, I don't know if that's feasible, but in theory, that is possible. So I don't think you can use that to guarantee. It's not as difficult as you think. Guys, they told me right here that the silver is being reduced. Like, look for that. Now, some people said, well, if I had a reduction table, if they gave me multiple half reactions, as long as the 0.8 was the most positive reduction potential, then I do feel confident in you saying that it had to be the one reduced. But the fact that you didn't have any other half reactions, I think you got to go back to the question, right? So my question then is, if we know that the silver is getting reduced, so we know that this number is going to be my reduction potential, I don't understand then how I can solve for that, but it's asking for the reduction potential of the unknown metal. How does solving for what I circled get me the reduction potential? Yeah, solve for the oxidation and flip the sign, right? And so this is what it would look like. You can put this on your last slide. Yes? My oxidation potential is equal to my cell potential minus my reduction potential. And that gave me the oxidation potential of negative 0.33 volts. But I flipped the sign. Now, if it actually asked me what the metal was, they'd have to give me a list of reduction potentials that I could then go look this up. So I believe it's copper, right, was the unknown metal. And I'm looking back at that previous slide that had all of the reduction potentials on it to get that. Copper is positive 0.34, so this was close enough that you could do that. Okay. And that concludes cell potential for voltaic cells.